Good morning, everybody. Good evening, wherever you are. And today, as Matt indicated, we have him in the background. We always also have our colleague Cici Martucci, who is monitoring the chats. So whatever you need, put it there. She is monitoring them, and we have two great interviewees, two great guests today: Ravi Rajamani and Matt Morin. Um, People who have been in the marketplace for a long time, who have written essay edge research reports. As a matter of fact, the mobility frontier is one of the activities that we develop because of the essay edge research reports, and they will talk about them in anyway. So the feel free always to ask questions, and feel free to come forward and put your views on the chat so we can let our speakers know about them and reply or discuss. We have about 45 minutes, which is plenty of time. And anyway, we'll start shortly, but the idea is to focus on aerospace decarbonization. Ravi comes from a background that is more on the electrification side. Matt comes from the hydrogen side. So let's see where we arrive today. So Matt, let's start with you. You have been involved with developing power and propulsion systems for quite some time. You worked at NASA for 30 years, being involved with the Space Shuttle program, the ISS, among others. And you have been involved with hydrogen, cryogenics, thermodynamics, thermal management, among other activities. So it seems that hydrogen has always been part of your career. Can you expand on it a little bit before we go to introduction to Ravi?
Sure, and thank you for having me here. Yeah, as you mentioned, I've been in power and propulsion development for about a little over 42 years now, and about 31 years at NASA. I also did work for Department of Defense and private sector companies over the years. And like you said, hydrogen, liquid hydrogen systems in particular, have been a common thread through almost all of that time frame, starting in about the mid 1980s. My background in it, it's been fascinating to watch the growth and interest in hydrogen and liquid, including liquid hydrogen, over the last few years, because it was very much a niche area very active in the space area with launch vehicles and rockets, but a lot less outside of that, or a little bit in the chemical industry, upgrading of fuels, and then the steel industry. But most folks were not very familiar with hydrogen, certainly in outside of rocketry and the space industry. So it's been very interesting watching that whole momentum, I guess, grow. So great to be here. And again, I'm happy to share what I've learned over those 40 some years, as much as I can still remember.
Thank you. Thank you so much. Ravi, now coming to you. You are one of the most eclectic aerospace engineers I know. You have worked at Meggitt, UTC, United Technologies Corporation, General Electric, and your interests cover data analytics, integrated vehicle health management, MRO, and electrified aircraft. Give us a roundup.
Yeah, thanks for inviting me, and it's nice to reconnect with Matt. Actually, I started off as a controls engineer at GE, working on gas turbines, both for power and jet propulsion, and then moved on to diagnostics. And then, as you correctly point out, I was at GE and then moved to Pratt & Whitney, and then said, okay, propulsion is great, but I think at the vehicle level, I need to learn something. So went to work for Meggitt before I started my own consulting. And Meggitt had a company that developed both the power systems, the power electronics associated with the aircrafts, as well as energy storage systems. So both lithium-ion battery systems both for the main ship battery and the electronic and the EBAT, emergency bat. So that's how I got interested in propulsion power. And
Mhm.
thanks to you, Monica, we got to write the book on electric aircraft, one of the first ones, I guess, and then
Yes.
also on the certification of aircraft systems. So I think that's electric aircraft system. That's one thing we're going to touch upon today. But
Yes.
interestingly, when you asked me about hydrogen, the first thing I did was, I mean, when I had joined UTC, that's the first thing they told me, that UTC, Hamilton, had been part of the space program. I'm sure, Matt, you know this, since the 60s, in the Gemini program. So, but then I read your colleague's book, Ken Burke's, not the book, his history of fuel cells in the space article, and that told me that it was not UTC but GE that was the first developer of the hydrogen fuel cell for the
Hmm.
Gemini program. So I've been associated with GE, which developed the first fuel cells, then with the UTC Power, Plug Power. Well, I suppose it was their fuel cell division, which was part of Hamilton, I think, and then became its own division that developed some of the fuel cells, the hydrogen fuel cells for the space shuttle program. So it's been a very interesting journey,
Yes,
personally.
for
And
both of you, as a
yeah,
matter
yeah,
of
glad to be here.
Yes, thank you. So let's start. So, even though decarbonization of the aerospace industry has been in the news, what can we say that is really concrete, that is happening right now, and that we can really say, well, this is a pillar that is being put on the ground, it has foundation, and it has a future? Matt, what do you think?
Well, I'll speak to hydrogen. I assume you want me to talk about
Sure.
that part of it.
Yes.
So where the traction really has been in hydrogen in terms of commercializing to other sectors outside of the space industry has been a lot in shipping, marine type applications, mining equipment, heavy duty mining equipment, trucking. You're seeing a lot more hydrogen trucks now being demonstrated. And aviation is, of course, as you know, the companies, of course, Airbus has been very public about their plans and very proactive. But all of the airframers and all of the engine manufacturers that I've communicated with have hydrogen programs at some level that are ongoing. Some are less public with what they're doing. Others are presenting pieces of it as they choose to. And then I think at the small scale, focusing now a little bit more on aviation, you've got companies like Zero Avia, who I think has been making very good progress towards small to maybe regional size aircraft. H2 Fly in Europe demonstrated a liquid hydrogen flight over a year ago now with a liquid hydrogen doer on board and a plane that had a fuselage with a pylon on one side and the storage on the other. And then recently, Joby just did a 500 over the 500-kilometer flight with liquid hydrogen in a electric vertical takeoff and landing aircraft, which is, I think, a very big milestone as well. So those are kind of the things I've seen that have come up within the last year or 2 years at the most that are very active, where you've got operational systems. I should mention too, trams and trains. More in Asia, South Korea has a tram that's operating. It's operational with liquid hydrogen as the fuel. So I think those kinds of applications where the hydrogen infrastructure can be concentrated and controlled by the organization that's running the vehicle, I think those are the first adopters that are starting to get some traction, because they can put those that infrastructure, let's say at the beginning and destination of their vehicles or ships or what have you, and not have to worry about the overall build out that you would for let's say a commercial vehicle or public transit.
Right. Ravi, would you agree? Would you see the
Sure.
same things?
I would add a couple of things to what Matt said. One is that, there is hydrogen. There's also actually ammonia, which is made with hydrogen, which people are using for ship propulsion. They're actually burning ammonia, which is interesting because that's less polluting, obviously, than carbon dioxide, hydrocarbons.
Right.
I mean, you have to be careful about how you burn it so that you don't make NOx, but
Right.
it is a bit, it's on the whole better. Anyway, the one other thing that I was going to talk about is there are two types, and I think Matt kind of mentioned it. A lot of what examples he gave was fuel cell based propulsion but a lot of companies are actually developing burning hydrogen directly in the gas turbine. So that's another way hydrogen can be used in aircraft. In fact, some of the older experiments, both from Russia, Soviet Union at that time, as well as Lockheed Martin and others, actually flew planes. They were even developing many experimental planes using hydrogen as a direct burning fuel in a gas turbine. But these days, as Matt pointed out, a lot of the focus is on liquid hydrogen, LH2, being used in a fuel cell to
In
generate
the fuel
electricity
cells.
and then
Right.
yeah. So it's kind of an
So
indirect process.
when we talk with other people who are in the business, they also say, well, if hydrogen doesn't work, or maybe concurrently with hydrogen, we have the possibility of the SAF, right? The sustainable aerospace fuel. Yet, once you talk about that, the first thing that we hear is, well, but there is not enough SAF to go around, literally. And even if I wanted to buy SAF today for my fleet, I can't find it. What do you guys make of it, Matt?
SAF is not in my area of expertise, so I'm relying on colleagues that I've talked to about it. I think all of these solutions all have their pros and cons, and I think you mentioned one of the ones that's been brought up about SAF. That are the feedstocks really sustainable in the long term as you start to scale up and potentially replace all the other aviation fuels that are out there? So that's one challenge. I think there's conversion challenges too, and creating the SAF. Again, speaking with colleagues about this, hydrogen is actually a feedstock for a lot of the SAF formulation. So you're already making the hydrogen in some cases. So I don't think there's any obvious clear answers and solutions that are fit across the board. I think we really, my personal opinion is we need to continue to develop all of these, let the marketplace decide in a lot of cases, and have public policies that are beneficial to the kind of experimentation and demonstration that's required to figure out which of these solutions work best for what particular applications.
Right. Ravi, what's your take on this?
So I mean, the way I see it, for the foreseeable future, the only way we can get sustainable flight for large aircraft is through SAF. The SAF is the only way to do it. There is no way you're going to have hydrogen. No way you're going to have electric aircraft carry 300 people. That technology does not exist today. So the only real viable way of doing it is using SAF. Of course, as batteries become better, as motors become more efficient, as power electronics, and you can get maybe even cryogenic hydrogen systems, yes, these other technologies will take over. But for long distance flight today, if we want to go sustainable, SAF is in my opinion, and what I've heard from propulsion companies, SAF is the only way of doing it.
So hydrogen then, Matt, would be more to short range aircraft?
I think in a near-term short range, and to Ravi's point, I think as you get into regional or larger aircraft, you just need longer development times to get those systems in place and the aircraft certified. And then, of course, they've got to enter service. They've got to be purchased by airlines and so forth. So I agree with his logic that, if you're looking for what do you put in place now, and then what is your long-term strategy, SAF as a drop-in fuel allows you to do that, because you're not making the kinds of modifications that you need to for liquid hydrogen at the airports and on the aircraft. But I think that the double-edged sword here is that you've got to continue that aggressive development if you intend to have hydrogen in 10 years, let's say, in large jet aircraft, which is what Airbus is proposing. I think their timeline is like 2035 for the first airport provided fueling for liquid hydrogen in their aircraft. So that is a very aggressive schedule when you start to look at the processes required to develop that. You have the standards in place. I know it's a part of what we were going to talk about today, as well as the infrastructure in place to do that. So again, to Robbie's point, I think there's a phased development here that heads us in the right direction, and continuing to do things as they're being done now isn't going to get us anywhere close to what we need to do, of course. So that's
it's for multiple lanes, right? That have to run all the time. And we have some questions from the audience. First one, do you see viable business models developing for fuel cell powered aircraft?
That is, may I?
Go ahead.
Absolutely, yes.
I mean, it's for short range, as Matt said, and I think I agree with him, that today is the only way of doing it. I mean, that's if you want to use hydrogen, you're going to have to use it through a fuel cell. Burning it directly is going to be tough. The problem with hydrogen is that even though it's extremely, extremely light, it's got very, very high specific fuel. I'm sorry, specific energy. It has got terrible volumetric energy, so density. So this is, in fact, it reminds me of a cartoon that I saw once where a 320-like aircraft was flying on, it was a hydrogen-powered aircraft, and behind it was another 320 size aircraft with full of hydrogen with the umbilical cord that connected the two.
Fueling it.
That's the only way you could actually get this viable. So that is a problem today. I don't know what else to say. I mean, today these things are all, I've done some back of the envelope calculations on the financial viability of all these eVTOL, electric, all these things. It's a tough sell, man. It's a very tough sell.
Well, there will be, and there has been a period of pure investment.
Yes, it is.
Investment, right, is going to pan out.
So many companies are going out of business, man.
Already.
Yeah, including Universal Hydrogen, which was the big.
Matt, what's your take on it?
Yeah, I would, going back to the original question, who's doing it? ZeroAvia is doing exactly, I think, what the person asked about. They're building aircraft that are using fuel cells and electric motors to drive the props, and they're flying demonstrations. Now they've got to develop, of course, commercial aircraft. To Robbie's point, just to give a little bit of numbers to what which he's accurate in terms of. You need 4 times the volume to have the same energy as a conventional fuel for hydrogen in liquid form. You need, but it has the same mass of hydrogen, has 3 times the energy as the same mass of aviation fuel. And then on top of that, fuel cells are at least twice as efficient as combustion processes. So there's a lot of variables there. But to Robbie's point, when you start to integrate this into an aircraft, you've got to have all of these in mind. You're going to have a larger form factor. You have to have a tank growth. Now your mass is going to be affected by you've got more energy per unit mass, so that's good. That helps with your payload and your cruise capability and your range. But you're going to have to grow the tank too. So the tank is going to get heavier. So how does that pan out? Well, it depends on the system. And I've looked at a lot of these systems, and they're all different. You have to look at what your driving requirements are and so forth. But to his point, it's really in a lot of ways almost a clean sheet development, other than you've got all of the typical subsystems and components in an aircraft. But when you start to get into the actual fuel, where you store it, how you deliver it to the fuel cell or engines when combustion engines are finally used for the larger aircraft, those all have to be rethought and redesigned from a very, I would say, well done systems engineering point of view, so that you really capture all of the figures of merit and all of your requirements and so forth, and get a performance both financially and technically that is viable for the market. So a lot of challenges.
Which is a very complex equation.
It is.
Yeah, right. So let's go back to Seth. We have another question. The person asks, how does sustainable aviation fuel impact industry decarbonization? Is it 100? Well, it will help decarbonize because it's not fossil fuel, but how does that work with SAF?
I mean, you're still going to burn it in the air.
Right.
You're going to get CO2. There's no doubt. The question is overall.
But less, right?
Yeah, it's the overall. From start to finish, you're going to use less carbon throughout the process of making it and using it. But you're still going to be spewing CO2 in the air. I mean, there's no way to avoid that.
Right. Yes.
So it is decarbonization on the whole, not decarbonization during flight.
For those that are interested, I'll just add the FAA, if you do an internet search, excuse me, has a graph showing different amounts of SAF in the airline industry and how it would affect the greenhouse gas production, carbon dioxide. But again, to Robbie's point, it's a hydrocarbon, so you're going to get carbon dioxide when you burn it. But overall, like you said, in the life cycle, it starts to reduce it.
Right. In the case of hydrogen, basically, you do not produce CO2, correct?
That's correct. When you either use it in a fuel cell or combust it, because it's hydrogen, there's no carbon molecule in the fuel, so there is no carbon dioxide output. Now, if you burn it in a combustion engine or in a turbine engine, you are going to create some NOx, and there's been work done to show how you can lower that and reduce it based on temperatures and your lean versus rich mixture of fuel to oxidizer. But any combustion process, it's a dissociation process. When you get into high temperature and combustion, you disassociate the air and it recombines into NOx. So there are no combustion processes I'm aware of that at temperature that don't produce NOx. It's a question of how do you manage that. But NOx is
how much of it.
Yes, and it is a greenhouse gas. So the fuel cell path doesn't produce any of that. It's all water vapor. So in terms of if you're trying to grade these in terms of what's having the least impact in terms of greenhouse gas production, fuel cells is definitely the gold standard in terms of you're just getting water vapor out. And of course, if you use water to produce the hydrogen, you've got a cycle there that closes on itself.
Right. No, yeah, absolutely. Now, I have a question for you, Ravi. What is the latest with electric propulsion trends for commercial and military aircraft?
So, as Matt mentioned, he mentioned Joby, he mentioned Zero Avia. I think those on the hydrogen side. On the electric side, I think some of the best work, and I've just returned from China, is actually being done in China, believe it or not. They have at least 2-3 programs that have been certified. In fact, EHang not only has a type certification, but it also has a production certification so they are a little ahead of us in this. Now, you can argue that it is EAAC giving the certification as opposed to FAA or EASA, but they are doing very well in that, what they call the low altitude economy in China. Now,
interesting. I like that.
Yeah,
low
altitude. So they are sort of combining the ground vehicles as well as the low these drones and other things for cargo, and also for sightseeing and other things, e-taxi kind of applications. So they're doing a good job there. Within our sphere, we have Joby, Archer, Beta, some of these, and then Vertical and others in the UK, and of course Volocopter and Lilium in Europe, who are doing they are making good progress towards certification. So when you asked how these are going to be viable in the civilian space, it is the first step would be the certification, when they can convince the authorities that they can actually fly these safely. Remember that a lot of these, Beta does not have it now, but the rest have all these tilt wing or tilt rotor technology. This is something that has never been tried in the civilian space before. So this is the V-22 or the new Bell helicopter, which have these tilt rotors or tilt wing technology. So this is something you'll have to actually convince the authorities can be
And us,
operated
who
safely.
eventually will be passengers,
Right.
right?
Yeah, I know you, and to be financially, economically viable, they have to take the pilot out of the aircraft. Because if you're paying a pilot and adding his or her weight to the aircraft, you are reducing the payload capacity. So again, like I said, I've done some back of the envelope calculations. To be actually viable fleet, you have to remove the pilot, which means you have a eVTOL, tilt rotor, new technology, completely autonomous. It'll take a while to get there.
Yes, it's a hard
Robo
sell.
plane. I like it.
I don't know much about the military actually, so I don't
Right.
want to comment on that.
Okay, Matt, anything to add?
It's interesting. When I give talks or presentations or training on this, one of my first slides is there's public information that I call the tip of the iceberg that's above the waterline. And then there's proprietary and confidential and classified information that is really the largest part of the knowledge base of most technologies, but certainly hydrogen.
Mhm.
And it can't be divulged. So there is military work, I can say, going on in the hydrogen area. You're not going to be able to get information on most of it for obvious reasons, national security and so forth. But I can tell you that there's a history of it with hydrogen. A lot of the contracts I've had over the years in my private sector work has been with military hydrogen systems. So, there are some things that are disclosed, but a lot of it is,
Isn't.
right.
Yeah. And we'll know who knows when, right?
And I'll add to that, though. One thing that is public knowledge is that in addition to, all of the armed services have goals in terms of, they don't call it decarbonization necessarily, but that's essentially one of the goals. But in addition to that, they add to that robustness of the system, the ability to be able to handle emergency situations or attacks.
Right.
So there's a whole nother layer of requirements that have driven them towards looking at hydrogen as a way to have that resiliency, essentially, not just in aircraft, but also in energy systems. And that's one of the areas where hydrogen is somewhat unique in that it plays in all these areas. And there's actually demonstrations in all of them as well, in terms of microgrids that are based on hydrogen or have hydrogen as a part of it, that take some of the offtake to fuel aircraft and fuel other things. So those are the things that some of the things that are going on in the military that's public knowledge that I can share. So
Right.
that intersection of all that.
For the military, basically, obviously, I'm not an expert in any way, shape, or form, but you always hear two things are absolutely essential: preparedness and resiliency.
Absolutely.
So
yes.
You have to fly when you tell you to fly, and in the end, you have to come back.
Yes.
Hopefully in one piece. So
right.
Basically, that's it, right? So right now, it's the last question from the audience. What are the most significant technological and regulatory challenges that need to be addressed to make liquid hydrogen and electric propulsion viable for widespread adoption in the aerospace industry? So,
yeah, you want to take hydrogen and I'll take the electric?
Yes, absolutely. Go ahead.
Go for it, Matt.
Okay. It's interesting. Again, my background has been, 40 years or so of liquid hydrogen systems. So one of the things I say that sometimes takes people aback a little bit is there's no enabling technology gaps in terms of the use of liquid hydrogen. These problems have been solved a long time ago in the space industry. Where the challenges remain is in, I'll go back to the systems engineering comment, is the systems engineering and development around now modifying what we know about how to handle liquid hydrogen and the whole supply chain that's already been in place again for 60 years, as you brought up, I think Ravi did, in the space industry, modifying that for commercial application, which means lowering costs, which means growing the supply chain, making more providers available in the commercial sector that aren't just providing to the space sector. So I think that's where the challenges are. Technologically, I don't see it as a technological problem. I see it as an engineering development problem. That's my personal opinion. Regulatory is a whole nother matter. I think that's where a lot of the challenges lie. Robbie touched on this with the tilt rotor stuff. I mean, you've got to get certified. You have to, regulatory can mean a lot of things, I guess. So there certainly is some. I'll broaden it if I can. The question a little bit to public policy. I think you have to have public policy advocating or putting in place the kinds of incentives and the kinds of environment that's required to be able to move forward with liquid hydrogen in any of these applications. There's certainly movement in that direction. It's going to lag, I think, and already is lagging behind the advancements that are already coming and the demonstrations that are already happening. So I think those are the challenges, along with the codes and standards that go with them, that we're really playing catch up a little bit in a lot of areas, because there's already demonstrators out there flying. Now we've got to have the codes and standards in place that allow regulatory authorities to be comfortable with their use. Yeah.
Right, where the touch points actually combine, right? No, totally. And from the electrification side, Ravi.
But just before that, I would say that the easiest for certification would be the SAF conversion, because that's, as Matt mentioned, it's a drop-in fuel.
Yeah.
A lot of the infrastructure already exists to transport it, to fuel it, everything. So I would say if you want to really talk about the easiest step towards decarbonization, that's through SAF. The next is, hydrogen is a unique beast, and it's as Matt mentioned, it's quite tough in many ways, not technologically, but I think safety-wise. What happens if there's a crash? I mean, you have hydrogen there. I mean, how are the first responders going to deal with it? Especially with a tank that's reinforced. What if it's a cryogenic system? What happens when that fails? There are a lot of issues with hydrogen. For electric, it's actually, to some extent, it's easier because we know how to deal with electricity much better. Of course, we are with electrified propulsion, we are dealing with much higher energy densities.
Yeah.
We're dealing with very, very, probably very high voltages, just to keep the currents lower and the wires smaller, thinner. So we have those issues to deal with. We did mention the tilt rotor and those models, which are, I guess, now being termed as powered lift, and FAA has just come out with a SFAR for that. And also for the pilot certification for these kind of new emerging technologies. In fact, there is a new technical committee that SAE just stood up, which is called G35, where we are developing standards for using models and simulation artifacts to be able to help the pilots, flight simulators, as well as type certification of aircraft. So using models and simulations. So this is a big deal, I think, and the two standards that are being balloted already, one for the pilot training, pilot training, and the other one for type certification using models and simulations through G35. And as Matt mentioned, there are standards are needed. And I think to some extent, SAE is doing a good job setting up technical committees to respond to that. You obviously know about E40 and AE7D and others that are developing standards for this new kind of aircraft. So that's
just to continue that a little bit, because in terms of infrastructure, airports and suppliers have a well-established system already for what we have right now, and so they can deliver on time and safely. Okay, what would have to change if we were to use SAF, hydrogen, or Ravi, as we had talked before, that there are some airports out there that are getting plug-ins, you know, the actual outlets, both for cars and for aircraft. And we said, is this safe? It's not regulated. So what's up with that? Matt, let's start with the hydrogen and then we'll go with Ravi again.
Okay. Yeah, so I'm part of a SAE hydrogen airport group, which is looking at exactly this challenge that you're talking about. Soon to be published, first document out of that group is the Aerospace information report on hydrogen fueling at airports, fueling stations. And then the next one in the hopper that we've just started talking about is coupling for high flow rates that are going to be required for the larger aircraft for liquid hydrogen. So there's progress going forward. As Ravi mentioned, SAE's out in front getting this addressed. The kinds of challenges that you start to look at, and we've been talking about for the last year plus that I've been involved, I think the task group was in place before I got involved, but is kinds of things like, you know, do you fuel in a similar way that you do currently? In other words, do you have, let's say, liquid hydrogen fueling trucks that come to the plane and then fuel it? Or do you have a stationary fueling station that airplanes come up to, and then you've got a stationary system that fuels? And there's benefits and drawbacks to both. It is not going to be like a normal fuel in terms of, or current aviation fuels in terms of the handling. You've got to handle that very low temperature that hydrogen's at. There's vaporization that occurs throughout the entire process you've got to manage. Again, this has all been done, but it's a change for the aircraft industry in terms of operations, and then maintaining fueling times that are complement or similar to what are current is one of the reasons we're getting driven towards looking at these high flow couplings is to be able to really fuel the planes fast enough, especially the very large planes, for long distance travel. So that's definitely where the challenges are. And I guess getting back to my previous point, to me, those are engineering and systems engineering type challenges. They're not insurmountable, but it's definitely a significant change from the operations at current airports in terms of fueling.
Yeah, and so that you know, you answered a question that we just had come in from the audience. What is the biggest problem in hydrogen fuel refueling compared to the conventional fuel in aircraft? I guess you addressed it, or do you have anything else to add?
Just to keep in mind, you know, you're fueling with aviation fuel a liquid that's in liquid form at ambient temperatures or normal temperatures. With cryogenic hydrogen at 20-ish K or slightly above, which is minus 253 degrees C, you've got to manage that temperature difference. That's the biggest driver, I think, for a lot of the challenges in terms of fueling is, and again, these are not unresolved in other industries and other sectors, but it's new for you know, airport operations, and
Right.
It's going to take a lot of transferring of knowledge, training of personnel for fueling. You know, someone who fuels with regular fuel, aircraft fuel, is going to have to go through some pretty extensive training to understand how it's going to be different when you're trying to load with liquid hydrogen. And then, of course, the on-aircraft systems are going to be different, and they're going to have to be handled differently. So there's a lot there, a lot to unpack.
There is a lot there indeed. Ravi, what's your take?
Interestingly, one of the things that we will, in the electric world, will also be challenged with is the thermal management.
Mm-hmm.
Because once you're driving those many electrons into the into a system, you're going to have cooling heat issues. So you will have additional cooling requirements for the charging, even in electric aircraft, especially fast charging. In fact, that's one of the things that is different from automotive. Automotive, you can in theory charges with the 220-volt system at home, AC system. But all the fast charging is all very high voltage DC, very high current systems. And those are, I mean, if in a vertiport, if you have a system where you have 3 or 4 of these things being charged at the same time, you'll have to think about the grid implications, the electric grid implications of charging with pumping so much electric energy into these systems all at once. I don't know if people have thought through this. I have had some discussions with people who say that, yeah, it's going to be tough. But again, aviation is not that big a sector in that sense. I mean, we at our highest, we will never be drawing that much electric energy from the grid as, let's say, the automobiles sector will. So in that sense, I think we are safe. In fact, I mean, on the flip side, we also know that on the carbonization side, we only contribute maybe 2 to 3% of the CO2.
That's about it. Yeah, that's what
emissions, because we are tiny compared to, let's say, the tankers, the big ships, the transportation. I think
ground
contributes a lot more.
Yeah. Right.
So in that sense, I suppose we are safe to some extent, but that's the wrong way of looking at it.
Yeah. But so from the airline's perspective, is there a clear advantage besides the fact that, you would be part of the solution, not the problem, and when it comes to carbonization or decarbonization? Are there good reasons to change from kerosene, aviation kerosene, to hydrogen or to SAF, apart from doing the right thing from the environment? I'm just saying technically, what do you guys think?
Well,
will it pay off? Will it make a difference?
If in theory, let's say all of the automotive industry goes to electric, then we now are probably 50% of the carbon. Aviation is producing 50% of the carbon.
Comparatively, yes.
So we will become a huge. So there is no way we can escape this. And I think you're right. It is the right thing to do, but it is also, even from a perception point of view, I think it's important for us as an industry to tackle these problems. There's no doubt in my mind about that.
Right. Matt?
I wouldn't claim to speak for the airline industry, not having that background, but I think in fairness, it's public policy that's going to drive them in this direction. I mean, there's no economic reason to shift to any of these fuels when you've got such a long history of an infrastructure already in place for the current aviation fuels. If we weren't trying to reduce greenhouse gases, I don't think there would be any incentive to do that. And I think probably on the horizon, perhaps again, getting back to public policy, the chance that there's going to be a carbon tax or something like a carbon tax for fuels across maybe multiple sectors is probably another thing I would assume the airlines are looking at and saying, well, we can't make this change overnight. We probably need to have some hedging to make sure that we are able to reduce whatever penalties or whatever the carbon tax ends up being, if there is one. But it all revolves in my mind around public policy. If there isn't the public policy in place, I don't think there's a change that occurs.
Right.
I agree.
Yeah, because when it has to be done, it has to be done.
Exactly.
From the perspective of the traveler, the consumer, does it make any difference? Again, I would rather fly on a sustainable aircraft, obviously. But from the pricing issue, ticket, airfares, prices in general. Would it make any difference if it's flying on kerosene, SAF, or hydrogen?
Well, I think you've got to separate out cost from the price that the flyer is going to see. The cost is going to be higher initially when you change to any new energy paradigm. So, and then over time, as you get to economies of scale, it's going to reduce. I mean, we've seen this over and over again in many technologies in energy and propulsion sector. So, if that, whether that's going to result in a rise in cost and how much depends, again, I think, on this public policy. Is part of it going to be subsidies for transferring over to these other fuels or electrification? Or is there going to be a carbon tax on aviation, legacy aviation fuels that raises their cost to be on par with these new ones? So if in lieu of either of those, if there's no public policy that helps to level the playing field, then yes, it would be increase the airline ticket price.
Somebody's got to pay for this, right?
Quite a bit, yeah. And
Always.
Time,
yeah.
The one quick comparison I'll make, I mean, if you look at solar and wind going back, say, 10 years ago, there were a lot of naysayers that said it would never be competitive, that it was too costly. And now fast forward to today, and it's the cheapest way to bring on new energy capability or power energy by far than any of the other options. All the legacy options are not even competitive anymore. And you know, whether any of these other solutions or options for current fuels is going to follow that path or not is a crystal ball question. But I think we have a history of being very bad culturally at understanding, you know, that kind of reduction in price that occurs when a new technology continues to develop over a period of years and decades and becomes competitive. It takes time, but sometimes the time can be very quick, like the renewable energy sector within a decade basically proved all the people wrong who said it was never going to be competitive.
Right. Yes. Ravi, any input on that?
No, I think he covered it very well.
Right. Okay. So, Ravi, in your previous Edge research report that you and co-author Anna Dietrich covered the challenges of certifying aircraft that would be either more electric or electric altogether.
Right.
There were, you know, you were very clear, there would be challenges ahead. Where are we at?
I think I mentioned a lot of this earlier. So, but I would say, when was that written? Two and a half years ago?
2.5 years ago,
yeah.
about three. Yeah.
I don't think any of those challenges have gone away. We still have the same things that we had listed there are still there. The one thing that the FAA has done is brought out this thing on the powered lift. There is a powered lift category in EASA. Over and above the other kinds of aircraft, because remember, these are combinations of helicopters and fixed wing, so they have to have a special. FAA was using a special conditions for this, and now they've come out with some more specific rules. I mean, I would say one of the things that we had pointed out in that report was the need for standardization on charging systems.
Yes.
We'd hope that we in the aircraft industry would not have that fight that the automotive industry did. I mean, they have like 6-7 different charging standards around the world, and you have to have adapters and stuff like that to actually charge. We thought that we could start off, and SAE did a great job starting this off, saying, okay, well, let's at least agree on a standard. Even that we couldn't do. So we have, I think, at least 3 different charging modalities within the aircraft industry. Different companies have adopted different systems. So that's kind of sad. I wish that had not happened, but oh well. So such is life. In terms of battery systems, we don't have that high power batteries in aircraft today. We have much lower power densities. So the certification rules for that have to be worked out for high powered battery systems, energy storage systems for propulsion. Again, I don't see, as Matt pointed out, no technical issues there. It's just a question of making sure that from a system perspective, these things are safe. We had pointed out that during a crash, you have to have certain standards for how first responders and second responders actually deal with the situation. And I don't know if much progress has been made in that direction so far. On the
I can
whole,
tell
I
you
mean,
that in the ground vehicle, there is training now for that
yeah,
because
so I
there are
mean, the
so
one,
many EVs.
and thank you for pointing that out, Monica. One of the good things we have going for us in the aviation industry that is that a lot of the problems have been solved by the automotive industry in
Right.
things like this. So we
Yes,
can borrow, and it also lowers the cost considerably for us.
for
So
that.
right.
Absolutely.
So there are a lot of advantages of being not the first, but a follower, a
Right.
technical follower in this area.
No,
So
no,
that's
I
a good.
get it. Yeah, absolutely. Matt, a question for you. Having worked with thermal management issues in space and aerospace, how quickly and safely could possibly address the necessary, could we possibly address the necessary changes to move from jet fuels, gas, and to hydrogen? Is there a timeline that is remotely realistically or no?
I think there is. We've touched on this a little bit too in terms of the challenges. If you look, I guess I'll point to the companies that have publicly done already. H2 Fly on a small scale with a small aircraft, and what Zero Avia is doing, and there's others as well, and Joby. They're not going to share everything, I'm sure, because a lot of it's proprietary and gives them their competitive advantage. But yeah, there's vacuum jacketed technology for tank storage, for transfer piping, for valves. Again, these have been around for 60 years at least in the space industry. Got to reduce the price. Got to, to Ravi's earlier point, standardization around components and interfaces is critically important for hydrogen systems as well. Just like the electrical systems, if you have 5 different types of interface connectors, then you just add the complexity that Ravi was just explaining is a challenge in the electrical side of things. So I don't think there's any technical reason why the timeline can't occur at a certain pace. I think it's really a question of funding and companies that are doing the development, and to some extent government funding of applied research and development in some cases to push it forward, and the standards development. I know that's a little bit of a roundabout answer to the question.
No, I understand, because these things, again, it's the crystal ball. You want to say, well, 10 years, and then it goes up to 20, or you say 10 years, and in 5 there is a breakthrough that, expedites everything.
Sure.
Ravi, any thoughts on that?
No, this
This
was good.
is it.
Yeah.
Yeah.
I'll add one if I can, Monica. Just one more comment on there, because we haven't touched on it yet. There is a lot of technology that is that now there's commercial companies that are putting out. Gen H2 is one that comes to mind, where they're handling vapor generation in a way that is new to the aviation industry, but again has its foundations in space, where you take any boil off and you reliquefy it, or you otherwise use methodologies to make it so that you're not losing that hydrogen and you're keeping your tank at a desired pressure and thermal conditions. So those kinds of developments, I think, too, are right there and ripe to be developed that not everyone is aware of in the aviation industry. I hear people a lot of times bring up boil off as an insurmountable problem, and that's not the case. It's certainly surmountable. It's just a question of how much complexity do you want in your system, and how much power does it take to give you that savings. So sorry, that's a little bit of an add.
Thank you. No, this is very important. Thank you for adding. So, final thoughts. Ravi, imagine this industry in 10 years. Where do you see it?
So I'm a skeptical person to begin with. However, I do think that for short distances, we will see something. We will see a air taxi maybe between replacing what they have between Manhattan and JFK, or in very highly populated areas, maybe in India and China and Brazil, you have these transfers to the airport using these air taxi systems that I think would be viable. It's so there will definitely be 3 or 4 certified aircraft, electric aircraft, eVTOL aircraft by then. So,
eVTOL.
yes. However, I think one of the developments that I think we didn't touch on were the hybrids. And the hybrids might be easier to certify and probably give that range that we don't have with the pure electric aircraft. So there is a niche there for
As we
very
see
well
with the
designed.
automotive industry, right?
Exactly. Where you can
It's
redesign the gas turbine to be small and very fast, so that you actually have very efficient generation of electricity, which then you use for propulsion. So that kind of serial is something that we may see more of. And but I don't see, as Matt mentioned, or actually as you mentioned, if in 5 years we get a battery system that is suddenly 1,000 watt-hours per kilogram,
Hey,
it'll
it
change
changes
the
everything.
entire industry.
Yes,
Today
absolutely.
we are still sitting at 200 and something.
Right.
So if 5 times the
Today.
energy density, it'll
Right.
completely change the.
Yes. Matt, final thoughts.
I guess I would just maybe introduce the idea, if folks haven't heard of it, of energy nodes, because I think airports have the potential for this if we go the hydrogen route. If you have a dedicated microgrid, one of the paradigm shifts potentially with hydrogen is you can produce the hydrogen, liquefy it, and have it all on site where you need it, when you need it. You can't do that obviously with current legacy fuels, where it has to be, drilled, brought up through the ground, refined, and then delivered. So I think my opinion, if I'm looking ahead a little bit, is there's going to be more emphasis on that. These microgrid systems potential around airports, and then you also have the ability to take offtake for other things like trucking, or maybe trains, other transportation modalities. So I would leave that as something maybe looking into the future, that may be an opportunity to start to play with some of the synergies that are available with hydrogen as an energy carrier, storage, and fuel.
Absolutely. Cannot thank you enough. This has been a great conversation. Thank you so very much. Thank you to the people that have been with us in the audience. Thank you to Matt Wazowski for putting this together and allowing us to use this platform. Cici for helping us with the chats. You guys were great. Thank you, Ravi. Thank you, Matt. It was a great conversation. Thank you so much. Until next time, until the next mobility frontier. Thank you.